Okay, our next topic deals with what we call nuclear bombardment. In nuclear bombardment, what happens here, and this was discovered by Ernest Rutherford, the same guy who discovered the proton and did that gold foil experiment that I talked about a little bit. He liked to play with alpha particles, and alpha particles helped him get to that point where he found out what a nucleus was. So what he did was he would shoot alpha particles at nuclei of atoms and destabilize them by doing it. So just like what they call an alpha gun, you start shooting these particles right at them. And an example of that reaction that he did was the bombardment of beryllium-9. Now, an alpha particle is just simply a helium nucleus. No electrons, just 2 protons and 2 neutrons. Hence the 4 for the atomic mass. What it would do is it would capture it and would destabilize the nucleus to create a new nucleus of carbon-12, which is extremely stable, but it would spit out a particle that turned out to be a neutron. Of course, at the time he didn't know it was a neutron, but suspected something was up here. Now, when we do this type of reaction, it's like what we've done before. We have to make sure that the top numbers add up to the same on both sides. 9 and 4 is 13, 12 and 1 is 13, 4 and 2 is 6, 6 is 6, so everything's balanced. And so alpha particles was the favorite, but it doesn't have to be alpha particles. It could also be protons, which is technically a hydrogen-1 isotope atom, isotopic atom. It could be neutrons, which we talked about, but that was a product here, but it also bombard nuclei with these neutrons, and we represent that with a 1, 0, and it increases the mass by 1, but does not change the atomic number, because the protons are not increased. Of course, electrons, generally in the form of beta particles, and we can also have deuterium. Deuterium, if you recall from way back when in Chem 1, is simply a hydrogen-2 isotopic substance. And then there's also tritium, which is an even heavier isotope of hydrogen with 2 neutrons in it, to give it a total mass of 3. An example of one like that where we use, say, a protium or proton is taking aluminum, 27. Aluminum 27 is the most stable isotope of aluminum, and shoot protium or protons at it, and it turns out that the new particle for this is aluminum 26, which is not very stable, and this will emit a deuterium, which is 2,1 hydrogen. Now the symbol, when we use, if we were to show this as a bombardment reaction, what they generally do is they'll take the target, if you will, what we're shooting the particles at, and then in parentheses we describe the particle that's shooting it, which is in this case a protium or proton. So we just use a P for that, symbol for that. And then the particle that's emitted, we keep in the parentheses, that's a deuterium, so we use the D as a representation of that. And then on the other side, we get aluminum 2613. So we have other symbols for this. So deuterium, we have a D. The proton, H1, we use a P. And for tritium, we use a T. So there are going to be some exercises that we're going to be asked to use or determine a balanced equation either in regular form or in bombardment form. Okay, so it turns out that a lot of transuranic elements also can be done this way. The cyclotron that's been developed is designed to create these particles that are larger than the most the highest mass naturally found elements. So we can create new elements by using this bombardment treatment. An example of that would be curium 242, which we could also write as this symbol. And what happens with that, this can be created by targeting a particular element, and we find that when this happens, we get a neutron, one neutron off of each bombardment of an atom. So the question could be, if we were using an alpha particle in the bombardment, then what was the target element? Okay, so we know alpha is He42, neutron is N10, and so we just simply write an equation and then balance it and see what we will need to have in order to create this. So this will be blank plus curium, I'm sorry, not curium, the alpha particle, He42, gives us the curium that we're trying to create here, which has a mass of 42. Now curium is element number 96, so there's 96 protons in there. And like we said, we know that a neutron is being created from this. So the question is, what is this right here? So we can go and through and balance the numbers at both the top and the bottom part. So 242 plus 1 equals 243. And of course 96 plus 0 equals 96. But we have here helium, or 2. So that simply means then that this element over here is going to be 4 less than that total that we have up to that point. And then we're going to lose 2 off of this. And so then of course it's going to create 239 on the top. And on the bottom it's going to be 94. Take a look at a periodic chart. You see that element number 94 rather, is plutonium. So we can write the equation like this. All right, so when we change this over to the bombardment form of the reaction here, this is going to give us 239.94 Pu on the outside. And the parentheses are the 2 particles involved. First of all, the bombardment particle that's hitting this target right there, and that's your 4,2 helium, better known as the alpha particle, which actually is what we should be putting down here. So put alpha there. And then inside is this neutron right here. We'll just put N there for that. And then on the outside is the result that we are creating in this bombardment with our cycloid, our cyclotron. So this is the overall equation. So the bottom line here is these equations are pretty easy to figure out if you can do basic arithmetic. Now you get up to the hundreds, maybe some of you need to use a calculator, that's fine. But this is a whole lot simpler. Now, when we get into the amount of heat being involved here, we're going to talk about that in the next lesson. But just to give you kind of a quick overview, scientists have decided to not use a mole of electrons in calculating these things as to how much energy is being created. So we use something called an electron volt. An electron volt is the amount of charge that one electron will have. Now, Coulomb, or Jacques Coulomb, a French scientist, came up with a quantity that wasn't as massive as the mole for the number of electrons. 10 to the 23rd electrons is crazy high. What he picked is also kind of crazy high, but not as bad. He said that 1 Coulomb, of course they didn't call it Coulomb, but they named it after him, has a charge equivalent to, or has the number of electrons equivalent to 6.24 times 10 to the 18th electrons. Okay, so the amount of energy involved in this that we're going to talk about in the next section is related to this quantity. So that means then that 1 electron has a charge of 1.60 times 10 to the negative 19 coulombs. And so when we're talking about atomic particles, we have to deal with a very small packets of energy that's involved in the creation of these things. These reactions give off an amazing amount of heat. We're going to talk about that in the next lesson. But this looks incredibly small because it is 1 atom. But when you put it to the mole sense, which is what we need to do in a reaction that when we did this in chemistry, this kind of thing in chemistry, when we had an exothermic reaction like a heating of a furnace or something, you're talking about thousands of kilojoules. But when these reactions take place and the amount of heat that's being given off, we're talking about millions and billions and possibly even trillions of joules of energy given off per mole. So just want to give you a little heads up on this. That's why it's on the script, but we're going to talk about it a lot more later on. So your assignment is on the sheet, and the PDF form that's accompanying this. It's not on the script. So have fun.